Hello, and welcome to today's lecture on the basic concepts of nuclear magnetic resonance spectroscopy, or simply NMR. This remarkable technique has transformed how scientists explore molecular structures and interactions. Whether you're a chemistry enthusiast, a student, or a curious learner, you're in for a fascinating journey into the atomic world. Let's get started. Hello, and welcome to today's lecture on the basic concepts of nuclear magnetic resonance spectroscopy, or simply NMR. This remarkable technique has transformed how scientists explore molecular structures and interactions. Whether you're a chemistry enthusiast, a student, or a curious learner, you're in for a fascinating journey into the atomic world. Let's get started. Nuclear magnetic resonance, or NMR, is a powerful analytical technique used to reveal the structure of molecules. By exploiting the magnetic properties of atomic nuclei, NMR provides detailed insights into how atoms are connected within a molecule. It helps identify functional groups, molecular arrangements, and even subtle differences in atomic environments. Beyond structure, NMR is crucial for understanding molecular dynamics, how molecules move, interact, and respond to changes in their environment. This makes it indispensable for studying molecular behavior, from drug interactions to protein folding. Essentially, NMR transforms invisible atomic interactions into clear, interpretable data, allowing scientists to decode the complexity of molecules with precision. At the core of NMR is the nucleus, the tiny center of an atom. The nucleus contains protons, which carry a positive charge, and neutrons, which have no charge. NMR specifically focuses on nuclei that have an odd number of protons or neutrons. Why is this important? Because these nuclei exhibit a property called spin. Spin is a fundamental quantum characteristic that gives these nuclei a magnetic moment, which is crucial for interacting with external magnetic fields, making NMR possible. So, what exactly is spin? Imagine it as a fundamental quantum property of certain atomic nuclei, almost like a microscopic dance or rotation at the subatomic level. This spin gives the nucleus a magnetic moment, essentially turning it into a tiny magnet. This magnetic moment is crucial because it allows the nucleus to interact with external magnetic fields, which is what we use in NMR. However, not all nuclei exhibit spin. Only those with an odd number of protons or neutrons have this property, which means they can generate a detectable magnetic moment. For example, nuclei like hydrogen 1, carbon 13, and fluorine 19, common in NMR studies, each possess a non-zero spin and behave like tiny magnets in a magnetic field. These are the nuclei that interact with the external field, making them ideal for NMR experiments. When we expose these spinning nuclei to a strong external magnetic field, something truly fascinating occurs. The magnetic moments of the nuclei align in specific ways. They either align with the field in a lower energy state or against the field in a higher energy state. This alignment creates two distinct energy levels for the nuclei. The strength of the magnetic field determines the size of the energy gap between these two states. The stronger the field, the greater the energy difference. This alignment is a crucial part of NMR as it sets the stage for the next step in the process. When we apply a radio frequency pulse, nuclei in the lower energy state can absorb the energy and jump to the higher state. It's this transition, driven by the magnetic field and the frequency of the radio pulse, that produces the signals we detect and analyze in NMR experiments. The real magic of NMR happens when we apply a pulse of radio frequency energy to the sample. This pulse is tuned to a very specific frequency that matches the natural frequency of the nuclei in the sample. when the frequency of the pulse matches the nucleus's natural frequency, a phenomenon called resonance occurs. At resonance, the nucleus absorbs the energy from the radio frequency pulse and moves from its lower energy state to a higher energy state. This transition is key to the NMR process. The amount of energy needed to excite the nucleus depends on both the strength of the magnetic field and the type of nucleus involved. Once the nucleus absorbs this energy and transitions to the higher state, it quickly relaxes back to its original energy state, releasing energy in the form of a signal. This is the moment we capture in NMR, the point where the nucleus speaks. The signals we detect contain detailed information about the chemical environment of the nucleus, such as its electronic surroundings and its interactions with nearby atoms. These signals are what we analyze to understand the structure and behavior of the molecule. Isotopes are versions of the same element. They have the same number of protons, but a different number of neutrons. This change in neutrons doesn't affect the chemical properties, but it does change the mass and magnetic behavior, which is important for NMR. In NMR, we focus on isotopes that can interact with a magnetic field. Here are some common isotopes used in NMR. Hydrogen 1. This is the most common isotope used in NMR. It's found in almost every organic compound because hydrogen atoms are everywhere. Proton has a single proton that makes it respond to magnetic fields. By studying proton NMR, we can learn about the hydrogen atoms in a molecule, like what they are attached to and how they are arranged. Carbon-13. This isotope of carbon is important in NMR because it has a magnetic property, unlike the more common carbon-12. In carbon-13 NMR, we can learn about the different carbon atoms in a molecule, like where they are and what they're connected to, helping us figure out the structure of the compound. Fluorine-19. Fluorine-19 is useful for studying molecules that contain fluorine. Fluorine atoms are very reactive, so they can change the behavior of nearby atoms. Fluorine-19 NMR helps us understand how fluorine interacts with other atoms in the molecule. Each of these isotopes reacts differently to magnetic fields, which allows scientists to use them to study the structure and behavior of molecules more easily. When we perform an NMR experiment, the information we gather is shown in a graph called a spectrum. In this spectrum, we see different peaks. Each peak represents a group of nuclei in similar environments within the molecule. The position of each peak tells us about the type of atoms and their surroundings in the molecule. By carefully analyzing these peaks, we can learn important details like the molecule's structure, how the atoms are connected, and even how many atoms are near each other. For example, peaks that appear close together might indicate atoms that are near each other in the molecule, while the intensity of the peak tells us how many atoms are in that environment. Let's take a closer look at the peaks. The position of each peak, measured in parts per million, shows us the chemical shift, which tells us about the environment of the nucleus. The way the peaks are split into smaller parts, known as coupling, shows us how many neighboring nuclei are close by. Together, these details give us a lot of valuable information about the molecule. To run an NMR experiment, we first need to dissolve the sample in a solvent. However, regular solvents can interfere with the signals we're trying to measure. To avoid this, we use special solvents called deuterated solvents, like CdCl3 or D2O. These solvents are similar to regular solvents, but with a small change that prevents them from interfering with the NMR signals. In addition, we often add a reference compound called TMS, tetramethylsilane. TMS has a unique signal that we use as a starting point to measure other signals in the spectrum. This helps keep the spectrum clear and ensures we get accurate results. To wrap up, NMR spectroscopy is a powerful technique that gives us a detailed look at molecules at the atomic level. By using principles like spin, resonance, and chemical shift, NMR helps us understand the structure and behavior of molecules. It has played a huge role in revolutionizing chemistry and is still a key tool in scientific research today, helping us explore everything from simple compounds to complex biomolecules. Thank you so much for watching. I hope this video helped you understand the basics of NMR and its importance in science.